Okay. So people, 9 people. Okay. So hello. So can you hear me? So okay. Hello. Maybe I have to wait until okay 30 and
They can probably hear you.
yeah, they can hear me. Okay. Okay. Good. And okay. And so let's wait more people and Q&A. Chat. Okay, let's look at chats. Okay. Uh, I can hear you. Okay, thank you. Yeah, I don't. Yeah. Hello, hello everybody, and uh, I didn't care. Okay. Yeah. Okay. And Santiago. Yeah. Hello, Santiago. Yeah. No. Okay. Hmm. Okay. Let's see. Hello. So I think you can write anything on the chatting uh, uh, panel. So you can introduce yourself if you. Yeah.
That might get a little bit
Yeah.
overwhelming.
Okay. So we have 1 minute left. Mm, what's this? Okay. Okay, so it's the time. So, okay, welcome to the Ask Me Anything session on Cork. And so the speaker is Adam Chlipala. He is from MIT. He's an associate professor at MIT, and he has been working on formal methods and software verification using Cork. But recently, also, his interest has been broadened, and he is interested in systems design and clean slate systems design and implementations. Okay, thank you. Yeah.
Thanks, Gil. It's great to be here. Have the chance to answer everyone's questions. I just want to mention cool things to prove with Calc include both software and hardware, and I like to spend time on both of those these days. So glad to have questions about either, as well as the mechanics of Calc and other formal methods tools, design choices for these systems, how to use them effectively, education, any of that. I'm interested in all of it. Fire away.
Okay. So you can type your questions in the Q&A panel. So
I think, Gil, you were going to start out with a question of your
yeah,
own.
okay,
Oh, by the way,
start.
someone just asked a question in the main chat. There's a separate Q&A session. It'll be
Oh yeah,
easier for us if you use that
right,
feature.
right. Okay. Is there separate question in chat? What's the one tool you? Okay, okay. This one I will. You can copy it and then in the asking the Q&A. Okay, okay. So show on stage. Okay. So the question is, what's the one tool you'd like to see implemented to make your life easier using Core? By Pedro Aburu. Yeah.
Tough question. I will start with a meta answer. I think in general, the issues that my group runs into with being productive with Calc mostly cluster into two categories. One is performance bottlenecks of proof automation, and another is just usability problems, bugs in complex features that apparently aren't being exercised elsewhere as much as we are. And it's not obvious how to abstract that into a one tool. I think a lot of people have been excited about good bridges with SMT solvers. And we have run into both those kinds of problems with Coq SMT solver bridges that, for instance, with bit vector goals, they just don't scale reasonably. If you wanted to say, do Hoare logic proofs about programs with multiple variables that are 32 bits wide each, things tend to fall over. So yeah, maybe a really solid performance scalable SMT solver bridge would be the natural answer here.
Yeah.
I guess I get to click a button that marks this question is answered. And
Okay.
oh, you clicked it. All right, fine.
Okay, so on stage, next question. Okay, so any recommended reading about the mistakes made in the design of LTAC? I heard a lot of people criticizing it, and there are new alternatives, MTAC and LTAC 2. How do these new stuffs compare to LTAC by Tesla? Okay, okay.
Right. You seem to be in good company. A lot of people agree with you that there were major design mistakes made for LTAC, but I guess I'm a contrarian. I think LTAC is pretty well designed. I would think it's better if you add an ML level type system to it, but certainly not dependent types. LTAC has just a really effective combination of features that you can plug together to build a whole lot of good stuff in a short amount of time. Now I'm actually curious who's using alternatives and for what out there, but it at least doesn't seem to be the case that people are voting with their feet and choosing MTAC over LTAC. LTAC too, because it just ships with Coq by default. I've seen people using it in real projects, though I don't have such a clear sense of the advantages of it. So I could totally believe it's significantly better than LTAC, but LTAC, I would also say, is a fine language. Sorry if you wanted more fuel for LTAC hating.
Okay, and then the first question actually I missed. I'll just show on stage. So the question is, any plans for a verified BlueSpec compiler by Haneli?
Oh, there's also an emoji with one drop of sweat on its face while smiling. I don't even know what that emoji means. How can I interpret the question? So I get to be a pedantic logician here and say, for literally the full BlueSpec language as supported by BlueSpec Incorporated, probably no one has the fortitude to do even a complete Coq semantics for that language. But we do have my group has our own alternatives, Kami and Koika, and the latter does have a formally verified compiler to Verilog. So maybe that counts as a yes answer to your question. I'm not sure, but definitely compiler verification deserves to be brought together with hardware formal methods, and there are actually several teams working on that now. For instance, one of Magnus Myrine's PhD students who's defending his thesis soon has a hardware compiler in the mix. So maybe this element of formal methods is further along than you realize with the question.
Okay, thank you. And next question is, what are the main differences from your book to Software Foundations? Yeah, the formal reasoning about programs. Yeah.
Okay, good question. So my book, Formal Reasoning About Programs, I will present a functional Perl about tomorrow. And basically, it's like an accelerated Software Foundations that assumes more about what people know at the beginning and gets further. And it uses various tricks to get rid of some of the rough edges that make proofs expensive to write. Like the subject of my functional Perl is a technique for encoding the syntax of programming languages that I'm calling mixed embedding that saves you from having to deal with the mechanics of variable binding and environments, but still integrates soundly with a general purpose proof assistant like Coq. So we use that, and we're able to get to some pretty sophisticated concurrent program reasoning techniques. We do, say, automated concurrent separation logic proofs about programs using linked data structures. And proof automation is another part of it that I just can't resist injecting anywhere that I'm using Coq. So through those several kinds of ammunition for the students, we managed to scale up further and see more cool stuff. But students entering the class do need to know what induction is. They're not going to learn it on the job with this class. That's you could call it a disadvantage compared to Software Foundations.
Okay, thank you. And okay, next question. What are standard way to prove liveness, like for consensus algorithm by Harold?
Unfortunately, I feel completely unqualified to answer that question. All I can say is if you have a well-founded measure that's respected by all the steps your system can take, then you've proved termination. That is about as far as my knowledge of liveness properties goes.
Yeah.
Can I think of anything else clever to say here? I probably can't. I'm sure you'll find other people who have published about distributed systems at ICFP recently who can answer that question better than I can.
Okay, thank you. And Mark has answered. And next question, it's a bit long. Could you elaborate on a little bit, objectively and or subjectively, about something that Coq brings to the table, especially with regard to dependent types, making it harder to develop a hammer for Coq? Yeah, yeah, like it,
I
and not
see.
like Mark. Yeah,
I think this is a question about advantages of Coq over Isabelle and implicitly over other proof assistants out there or that we can imagine being built. So maybe I should abstract this to a question about dependent types. Why should we build proof assistants on dependent types? I would not say it is obvious that we should. The community is still figuring this out, but I'll tell you some of the things I like about dependent types. And some of this you could even get with less expressive type systems, but that are still, say, beyond what we expected from Haskell and similar languages in the 20th century. Some properties have proofs that very directly follow the structure of the programs that manipulate those types. Whenever that's true, you can get a heck of a lot of mileage out of using type checking to establish those properties. So let's call these shape properties, like lengths of lists. Sometimes it's a good deal to use dependent types to track those. Sometimes it's a nightmare. Really depends on the setting. But when it works so well. And to me, it's also the Curry-Howard correspondence, where we represent proofs as lambda terms with a dependent type system, leads to a really pleasing, simple description of what is a convincing proof. And it's kind of nice to be able to reason about proof producing procedures by having one language that where the same grammar production contains both programs and proofs, though it also brings lots of complications. But I would also answer your question. There was one subpart about dependent types make it hard to develop certain automation tactics. That could be true at the same time as it's not a big issue if we just only apply those tactics to examples that aren't so dependently typed. And I do try to push my students towards using dependent types sparingly. I like to put it as, imagine every time you wanted to introduce dependent types in one module of your project, you had to fill out a bunch of forms and submit them to a bureaucracy, maybe have some hearings, go through an extensive process to get permission. And if you get through all that and it still seems worth it, then maybe you should proceed. But by default, you don't want to use dependent types. Explicitly, I mean, because under the hood, all the proving stuff in Calc uses them, but we don't have to see that, so it's okay. Okay, that's my long-winded answer.
okay, thank you. And the next question is there anything from other proof assistants that you wish it was in Coq?
Oh no, this question will expose my tunnel vision. What can I think of here? It certainly does get aggravating when people say that proof automation built into Calc isn't as good as in name other proof assistant. So maybe we should be lifting some ideas from particular Isabelle, maybe ECL2, those kinds of systems. Though I don't find this to be an issue for people who've gotten at least moderately far along their learning curves with Calc. Man, I'm having trouble thinking of what else I might want to say here. So I have minimal firsthand experience using other proof assistants, so I don't have a great source for visceral positive reactions to things. But if anyone has other proof assistant has an approach to scriptable automation that just by default tends to have good performance scaling, that would obviously be worth stealing. That's my main issue with Coq. End of answer.
Okay, thank you. And then, okay, so what is the 2021 way of doing PL meta theory in Coq, especially with respect to binding representation by Julia?
I don't think there is one standard way. It really depends on what kind of development you're building. For instance, if you're working with any kind of object language that is very naturally interpreted as a subset of the meta language, called Scalina, then it works super well to write essentially a definitional interpreter that takes in terms of your AST and just produces native functional programs. And then when you do that, I really like the parametric higher order abstract syntax encoding that I developed. Everything just works really smoothly. But if you get into any setting where you want to think about substitution explicitly, then that encoding does not work well, and things seem to get fundamentally more painful. So I will take this opportunity for a public service announcement. All the students out there who think it's going to be a small, fun excursion to add to your thesis some meta theory proofs in Coq. There's a good chance it's fun, but it's not going to be small. This is still a research frontier. I don't think people are yet routinely doing meta theory and not spending any time thinking about how to do meta theory versus learning about the actual properties and languages that they meant to study. So be careful of this sort of thing. Life is a lot easier when you pick languages that are easily embedded in the meta language, that don't use new effects that you don't have there. And there's still room for plenty of ICFP papers smoothing out the proofs of other kinds of systems.
Okay, thank you. Okay, next question. Do you think Coq is a good tool to introduce proof assistant to undergraduate students? I'm aware of a couple efforts targeting specifically this task. And this seems like a better bet than the most powerful tools like Coq. By our time.
The tricky thing about this question is it does not specify what is the objective towards which we might deploy the tool of teaching students Coq. I have found that when I offer a class on formal reasoning about programs using Coq, the undergraduates who choose to take it tend to do pretty well with Coq. It's not obviously a mismatch with that audience, but it's a very self-selected audience. I wouldn't do it in a class that every CS major has to take. So, for instance, in my book, I develop kind of an alternative baseline tactic library. We write induct instead of induction, and a fewer surprising things happen in the course of the semester. So I'll put it this way. For people who are headed towards careers applying proof assistance and related tools in the real world, I think it's quite appropriate for them to start using Coq and other full-scale tools as undergraduates. If you have other goals like just teaching discrete math and having people never touch proof assistance again, and you want all the CS majors at your school to have that experience, I think you're right. You don't want to use Coq. And there have been some good results using ACL2 there at your own institution and maybe some others out there. I think the community is still converging on what tools, if any, to use in that sense.
Okay, thank you. Okay, so next question is, there's a lot of verified compilers, but no unified Coq framework for writing verified compilers. Is there good reasons for that? By left.
Probably. Compiler is a deceptively uniform sounding term. There are so many different kinds of compilers. It's hard to imagine one framework that's a good fit for all of it. Even just being able to abstract over different language syntaxes is a pretty heavyweight kind of operation, which you very rarely want to experience. For instance, Turing complete versus languages that are very easily viewed as subsets of Calc itself. I think you probably want completely different approaches to semantics and compiler verification between those cases. But at the same time, there's a lot of interesting work left to do about reusable frameworks, some of which I've been looking at with my students lately. And I'm sure other people have too. I think we could say at least one of the papers that was already presented at ICFP is in this category. So don't give up hope.
Okay, thank you. Okay, so next question. Any opinions on sprop versus prop? No opinion is valid answer. Okay, and do you think it's a good idea to replace prop with sprop by Tesla?
Is sprop the one or the other is the proof irrelevant versus not proof irrelevant version? Is that right? I'll just wait for a chat answer.
Yeah, chat
Hopefully
answer. Okay, let's see. Chat.
Yeah, okay. Yeah, I haven't yet seen any place that this matters for computer science, and I am not qualified to speculate about applications in math. So I don't think I have a great answer, except for computer science, I'd prefer not to have my proof assistant complicated by this distinction because it makes the trusted checker larger and more likely to have bugs in it.
Okay, thank you. Okay, a lot of questions. So, what process do you recommend for hunting down standard language tooling that is absent from the Coq standard library, or at least lacking the proofs of obvious facts? By Joshua.
I actually think that the community doesn't have enough clarity yet on basic software engineering kind of issues for Calc developments to know what libraries should be presenting. There are research questions in the way of agreeing on standard libraries. And so, honestly, all the stuff you need about maps, you can write yourself in a short amount of time. And for research where you're not trying to build a product on a deadline, I think that tends to be a good choice. What the Calc standard library is really missing for maps is maps with canonical representations, so you can use equals to describe the algebraic laws you want for maps. So my group has a utility library where we have that guy, and but I think it's not obvious everyone out there wants that. So I don't know what a good standard library looks like. I think it's a little too soon to try to converge on that.
Okay, thank you. And okay, how close is Coq Galena to CIC? Is the development of Coq making its core theory diverging from CIC by Tesla?
It's kind of a philosophically tricky question. How do we measure proximity of a big old OCaml code base with a theoretical lambda calculus? Like the module system is not in CIC. That's one that I worry about. In general, I'd like to see a mode of Calc elaborating into the smallest core language possible so we could have a separate checker for that language with less risk of bugs. What else is there are all these performance optimizations, like representing an application as function and then a list or an array or something of arguments. Probably at some level say that's not in CIC. And then co-induction is another one that, depending on how you define it, we might say is or isn't in CIC, but it's also easy to avoid using co-induction. But there's this primitive projections feature. I think we can split all the features into, you don't really need to use it and you'll be fine. And there should be an okay approach to elaborating it into a core language that doesn't need that feature, which is a totally useful thing to do, especially as we head towards a world where proof assistants become safety critical because they're used increasingly to check safety critical systems. We should have an elaborator into a core language and a separate checker for it.
Okay, thank you. Okay, right. Okay. Okay, next question. What was the most important contribution in PL in the last 10 years, in your opinion?
Oh gosh.
This is a general question.
I don't. Is this a trap? Can I say anything without offending someone? And I have to orient myself on which years were the last 10. Okay. Well, it lines up conveniently with when I started as faculty. That's a very useful marker for me. But still, important contribution to PL. I'm definitely. I don't think I'm going to be able to answer this question directly. Let's see if I can pick some projects that I want to call out because I think they're super cool. I think the CakeML project is super cool and relevant to the subject of this AMA. Some really solid work on the complete stack of software and hardware tools that go into real systems. I guess the Cell 4 verified operating system had its first paper a little before this period, so it doesn't count. Probably people are more likely to realize it's awesome. Anything else I want to call out sort of related to this topic, just as a tiebreaker, so I don't have to make as many judgment calls. I think I won't list any others because then I just get myself deeper into the hole with the ones I forgot to list.
Okay, so okay, and the next question. Do you think type class is a good language feature? In math, the definition of ring requires two groups with different notations. In Lean, they duplicated the definition of group with different field names. Do you think it's a good idea? By Tesla? Yeah.
I think type classes are a great language feature. Again, I don't have personal experience with mechanized proofs of math, so I don't know what works there and what doesn't work. I do know that in the kind of parameterization you do for PL sorts of developments like compilers, we have experienced a lot of pain in the right way to set up the plumbing, and type classes are not the silver bullet there, at least as far as we figured out how to use them. So there's some soul searching left to do around how to do parameterization well in significant developments with complex hierarchies between the different modules. Type classes might be part of it.
Okay, good. Okay, thank you. Okay, and so what is the future of your? Is it right pronunciation? Okay.
I say
Okay. Do you know if someone could write an airmeet in it? Okay, provided funding and time, or it gets a bit slow to catch up with the modern web.
So erweb is my domain-specific language for web programming, and I can't immediately think of a reason why someone couldn't write something like airmeet in it, especially because there's a foreign function interface. That might be kind of a cheating answer. If you use that, then you're not obviously getting all the nice benefits of a carefully designed DSL. And heck, I'm trying to use erweb to build real stuff. Let me know if you want to learn more about my startup doing that. But let's call that off topic for the rest of this AMA, though.
Okay, thank you. Okay, and what tricks do you use to speed up automation and type checking? Example, avoiding some tactics, splitting into more modules by Julia. Okay.
The mother of all tricks is to find ways to get all the real action to happen in reduction of Galena terms. Basically, use proof by reflection or similar kinds of techniques. That's really the only way we've found to get predictable performance in automation. There's apparently some fundamental bottlenecks in the Coq proof engine, maybe also the Coq type checking kernel. And we think that's an interesting research direction to look into, how to improve those. Do I have any other big tips here? Try to avoid having huge sub goals. That makes everything slow. And splitting into more modules, well, I guess in general, if you can decompose a big theorem into many lemmas, that will tend to improve performance because you don't have as many huge sub goals anymore. And it's also easier for people to read, so it seems like a win-win. But of course, we know it's hard to think of good modular structures, so it's not always going to be a good cost-benefit trade-off.
Okay, thank you. And so I think that's all. Oh, there's one more. Okay, good. Okay. So I'm impressed by today's talk on verified LLVM IR using interaction trees. Do you see any domains you'd want to apply them, for example, hardware, or how do you feel about them in general by Artem?
Yeah, I think interaction trees are a cool formalism, which I've been using for a while. And would we want to use them with hardware? I'm not sure. I think hardware might be somehow simple enough or first order enough so that the payoff doesn't really materialize. Um, I do think the community hasn't settled yet on what is the perfect semantics technique to use for these sort of settings, but interaction trees have a lot going for them of bringing some of the advantages that we associate with denotational semantics into more settings without having to deal with distractions like domain theory. And they're a very good match with a lot of well-loved functional programming ideas, so I'd certainly recommend everyone look into them.
Right. Agree. Okay. So and so I think we are. Is there any more question? It's just almost time. We are so 1 minute left, and so Adam, do you want to say anything to conclude?
Do I want to say anything to conclude?
There's one more question. Do I
All
take this
right,
one? Okay.
go for it.
Okay. Do you plan to work on developing better proof engineering practices?
I think this is what everyone doing research with Calc is forced to do every day to survive. And I plan to keep doing it.
Yeah. Okay. Good. Okay. Thank you. And so I think it's a time. But Adam, you can say any words.
Let's see. Um, check out my talk tomorrow, Functional Perl, based on my online book, Formal Reasoning About Programs.
Hmm?
I hope it's useful as a resource to learn more about kind of power user approaches to programming languages. And glad, especially, to talk to people who might want to use it to run their own courses.
Okay. Thank you. Okay. Thanks to
Thanks,
Adam.
everyone.
Okay. Uh, we now how the mod